Well, in this video series, we're going to go over chapter 2.6. We're going to be looking at two quantitative variables and linear regression. So we started looking at two quantitative variables with correlation in 2.5. We're going to kind of continue that idea going on to 2.6 with linear regression. So in this section, we're going to go over the regression line, using the regression line to predict values, define, look at examples of residuals, interpreting the slope and intercept of the regression line, and then we'll kind of look at some cautions and drawbacks of using the regression line for predictions. But first, let's take an example with crickets and temperature. Can you estimate the temperature on a summer evening by just listening to crickets chirp? So let's look at some data. We've got 6 or 7 data points here, 7 data points. Got a scatter plot. On the x-axis, I plot the number of chirps. This is chirps per minute. And on the y-axis, we have the temperature. So you want to think about that chirps we're going to think about is the explanatory variable. And then could we use the number of chirps to predict the temperature on a summer evening? So don't forget, the x-axis is almost always going to be the explanatory variable, and the y-axis will be the predicted or response variable. All right, so we want to come up with a regression line. The goal is to figure out a straight line that best fits the data in the scatter plot. So if you can imagine, we lay out a straight line. There's no straight line that'll go through every single data point, but hopefully you can kind of visualize a line that will best go through as much data as possible. And then be right around here. So we got here a line of best fit. We got a couple of data points that are very close to the line. A couple data points are a little farther away, but they're fairly close. Hopefully you can see how if we had a negative slope line, it would be kind of dumb. It would not fit this data at all. So we're going to generally write the estimated regression line as a y hat equals a plus bx. And here that x is going to be the explanatory variable, and y is going to be the predicted response. We're going to go over to these parameters a and b later on, but this b is your slope, and this a is your y-intercept. So generally in statistics, this form is used, but this is the same equation of a line as you're used to, the y equals mx plus b. All right, so the regression equation can be used to predict y for any given value of x within reason. We'll come back to that later in the series. But that line in the previous slide could be written as, y equals 37.7 plus 0.23x. And a lot of times, these regression lines are written like this. Instead of x and y, you can actually put the predicted variable or abbreviation, so temperature with a hat on top of it. And then the explanatory variable would be written as chirps or chirps per minute. So that's given right here instead of x. So if you're given this equation, if you listen to hear crickets chirping about 140 times per minute, what would be your best guess at the outside temperature? You just plug in 140 into chirps, so 37.7 plus 0.23 times 140. Throw that in your calculator to get 69.9 degrees, so about 70 degrees. All right, what is the predicted temperature when crickets chirp 103 times per minute? In the same analysis, you would take 37.7 plus 0.3 times 103. That's why I kind of like this notation statisticians use, because then you don't have to keep track of which variable is which. That's given here in the formula. And the predicted temperature in this case would be a 61.39 degrees. All right, the predicted response is on the regression line directly above the x value. So if we were to take 140 degrees, the first example we looked at, then the predicted output is, that was about 69.9 degrees. So it's good to be able to visualize with just looking at the line, but I also expect you to be able to enter values into the regression equation line. So kind of two ways to approach this to get an intuitive idea just graphically, but also I expect you to be able to plug in predicted values into your line of best fit to get this more exact 69.9 degrees Fahrenheit. All right, if the crickets are chirping at about 180 times per minute, what would be your best guess? Suppose you don't have the equation. If you just use the graph, what would be your best guess? And hopefully you're looking at the 180 on the x-axis. Go up to the line, and then go up over here. It looks like it's going to be about 80 degrees, 79, 78, 80 degrees. So not exactly 80, but out of these three options, 80 is the closest. But again, if you have the actual equation, you can plug this number to the equation and throw it in your calculator and solve for the exact predicted value. All right, so we want to look at the differences. How far is your predicted from the observed value? So one of the cases for this cricket data set is for 103 chirps per minute. The degree on that night was 63.5 degrees. So how far is the predicted temperature from the observed temperature? All right, so we actually calculated the predicted already. So 37.7 plus 0.23 times 103. Here is my predicted temperature. But our observed temperature was 63.5. So calculate the difference of these two. The prediction was off by a little more than 2 degrees Fahrenheit. So pretty close, good prediction, but it's not exact. And I want to go over this example because this is how the regression line is created. This is how it's defined. How do we figure out the equation for the best line of best fit? Is to use the idea of predicted and actual values. So the observed response value y is the response value observed for a particular data point. So we only have these observed values if it's actually given in the data set. The predicted response we're going to denote with a y hat. So y is observed response value, y hat is predicted. And this is the response value that would be predicted for a given x value based on a model. And in the realm of mathematics, you can plug any x value to get a y value. So you can make any predicted value. We'll explain later why sometimes this doesn't make any sense. But in principle, you could calculate a y hat for any input value, whereas the observed values, we only have those for the data that we know for sure. So the best fit line, the line of best fit, is that which makes these predicted values closest to the actual values. So basically we want to figure out, minimize the difference between these for our data set. So let's go back to the chirps versus temperature. Let's look at one specific data point. So this was, about 104 or so. This is 103 chirps per minute, and the predicted value. So this right here, this dot is the observed value. The y hat is the predicted value. All right, we figured these out in the earlier slide. And the difference between these two, let's go back. The difference between these two was the 2.11 degrees. So we're going to call the difference between these two the residual. The residual for each data point, we're going to define to be observed minus predicted, which in our notation is y minus y hat. Visually, you can think about the residual as always going to be the vertical distance from each point to the line. So if you look at this point up here, it's going to be the distance from the point to the line. And if we go down to this bottom value here, the predicted value is going to be the distance from the point to the line. But notice here, the residual is going to be negative. Since the dot is lower than the line, we're going to get a negative residual. All right, visualize that again. Here's the residual for the 103 chirps per minute. And we went through this calculation a couple slides ago, but this residual value, this distance, the observed minus the predicted, is 2.11. So the goal, the way to create this line, the mathematics behind this line, is to come up with the slope and y-intercept that makes all these residuals as small as possible. So then how would we measure this? This is created with something called a least squares minimization. So the least squares line is a line which minimizes the sum of the squared residuals. In notation, we would take the sum of all observed minus predicted values squared. Now the reason why we square these values is we want to make sure that distance is minimized, and it doesn't matter if the observed is above or below the predicted value. So let me go back to the data plot. So we want to minimize this distance, but it doesn't matter that the dot is above the line or below the line. We're trying to minimize the distance between the dot and the line. And we're going to rely on technology for finding the least square line. The last couple videos in this lesson is going to be going through how to use Stacky to come up with the line of best fit. That's the software we're going to use, but there's many different software that you could use to get the line of best fit. And just note, if I say, or if you read least squares line, line of best fit, regression line, they're all the same thing. The line that best fits the data. So just to visualize again, the idea here is we want to minimize all these areas, because you can think about the distance between these two squares. So I've got a little area, little square right here. So notice I've got 1, 2, 3, 4, 5, 6, 7 squares. And go back. And the mathematics behind this involves really about a year of calculus or semester of linear algebra. So the mathematics is a little bit outside the prerequisites of this course, but I just want to let you know it's not highly advanced math, but it does require a little bit of calculus or linear algebra, which we're not going to cover. So that's why we're going to use technology to come up with this line. But the idea is to minimize these squares. All right. And like I said, I'm going to have a couple more videos at the end of this lesson going over Stacky in more detail. But what you see right here is a graphic of a line of best fit, regression line, and you have a bunch of information right here. So you don't actually, Stacky doesn't directly give the equation, but it gives you correlation from 2.5. It gives you the slope and the intercept. So if we're going to write the equation, since this is temperature, the y-axis is temperature, so I'll do temp with a hat on top of it, equals the y-intercept, 37.679, plus the slope, 0.231, times the x variable, but that x variable is going to be the choice. So you can also write this as y equals 37.679 plus 0.231 times x. So intercept plus slope times x.